Alright, this is part 2 on section 2.2. This video we're just going to look at some derivatives through piecewise functions and how to make something differentiable. So, example number 4. We want to figure out if this function is differentiable at a specific point. Differentiable just means that the derivative exists, and it's going to be a piecewise function. So kind of going back to the concept of like continuity, we had to check the continuity, the limit from the left and also from the right. We kind of have to do the same thing for derivatives. And the notation for the derivative from the left is going to be pretty similar. I'm just going to put a little negative sign. It means the derivative from the left of 1. And somehow that's going to have to equal, I'm going to check to see if it's equal the derivative from the right. Okay, so the derivative from the left, that's going to be the derivative of this, which, going back to my handy dandy derivative rule, says this derivative constant is going to be equal to 0. I can just take this negative 2 and multiply it by the derivative of x squared, which is going to give me negative 4x. And somehow that's going to have to equal the derivative from the right, which is the derivative of this side, which is going to be 3x squared minus 6. And so when I evaluate the derivative on the left at 1, that's going to equal negative 4. I want to see if that's going to equal the derivative evaluated at 1 from the right, which is going to be 1 squared minus 6. So this is going to, let's see here, this is going to be 3 minus 6, which is going to be negative 3. That definitely is not the same thing as negative 4. So the derivative on the left does not equal the derivative on the right. So I can conclude that this is not differentiable. So what this would mean is that the derivative would not exist at 1. And tomorrow in class, what I could do is show you guys a graph of this piecewise function and zoom in around 1 to show how the derivative would not exist at that point. Example 5 is going to be dealing with another piecewise function, but this time we want to find the constant to make it differentiable. Well, to make it differentiable, I need both of these derivatives to be equal to each other at the point of where they're being split. So basically h prime from the left is going to be 2x. And if I find h prime from the right, well, m and b are just constants. So the derivative of this constant times x is just going to be really just m. So what I want to do is I want to evaluate the derivative at 2, and that's going to give me 2 times 2, which is going to equal 4, and that needs to equal the derivative evaluated at 2 from the right. But since 2 is being plugged in for x, this is always going to give me a value of m, so I just kind of found what m is equal to. So m is equal to 4. Alright, so I'm halfway done. Now I have to just find out what b is equal to. Well, there's a handy dandy fact of life that I could use, and that's going to be that if a function is differentiable, then it's also continuous. Okay, so because it's differentiable, I could also assume it's going to be continuous. And kind of going back to the previous chapter, the fact that it's continuous means that the limit from the left needs to also equal the limit from the right. So now I'm going to use a limit approach from the left towards 2. And that's going to have to equal the limit of 2 from the right. Well, the limit from the left is going to be 2 plugged into this, which is going to give me a 4, equal to 2 plugged into this for x times what I found for m. So it's going to be 2 times the m, which is 4, which is 8, plus b. I can subtract this over to get negative 4 is equal to b. So I found out my two unknowns, m and b. One I used differentiability, and the other one I used fact of life, that it's also going to need to be continuous, and continuity, limit from the left, limit from the right, got me the other unknown.